Yeah. Our goal, well, it's easy, maybe. Nap time, no. Homework, no.
Yeah.
I'm not lying.
Look at him go. He gave
Well-
homework up for lunch. No.
Yes, that's a good idea.
That is a great
As
idea.
long as we get a good solid 84 minutes, whatever it takes to get this done. No,
All
it
right,
won't all be
everyone,
lecture.
shut up.
we got a kind of a group activity or a partner activity to do at the end too. So, but yeah, then we won't have any homework. But I do want to, I do want to go over into some detail on the homework assignment. Okay? Yes, I'm recording. So, we really need to finish up with this notation. There are several other questions I want to go over, very detailed, 38, 61, 72, or no, 62, 71, that I want to talk about because there's some things in there that are pretty important. On this, we need to emphasize, again, what this means. Can somebody tell me what that means right there? Can we take a crack at that, Steve?
Okay, it means the area beneath line, curve, whatever, function f of x
Right.
between the function and the x-axis between the x values a and b.
Okay? Now, something he said there that's very important, and we'll see if you remember it later today, that he said between the function f of x and the x-axis. Okay, now, a lot of times we'll just say the area under the function f of x, but what we really mean is between the function f of x and the x-axis. Okay? Now, that's very important. Now, this part, the f of x, that's like y equals, that's your equation. Well, that's what we have here. So all they wanted you to do was set up the integral. So it was very simple. All they were looking for was this for number one in the packet. That's all they wanted. That you understand that that area it is written as the integral from 0 to 3, or excuse me, 0 to 5 of 3, the function 3, and then the dx is just something we tack on there. The dx is just something we tack on there.
Too late.
So the 3 is, the dx is just something we tack on there. Hats? The dx is just something that we tack on at the end. Don't worry about it. Just make sure you put it there. And it just, right now, it just means with respect to x. But it will have some meaning later on. But right now, it just means that the variable is x. All right, so likewise on number 3, it's just the integral from -4 to 4 of the function, and then a dx. And that's all you had to write. You just set up the integral. Because what we're going to do, if you think about what we did with derivatives, we learned about slope, we learned about this idea of a derivative, we learned all these rules for derivatives, then we learned how the chart worked, and how that f and f prime had these relationships of increasing, decreasing, concave up, concave down, and then how we could apply that in problems to find maxes and mins and related rates and all that stuff. We're going to go through that same process. And the tough part in chapter 4 was setting up the problem so we could do the derivative. Well, the same thing is going to happen in this half of the class. We're going to talk about this idea of area. Today on 38, problem 38, we're going to talk about Cartog, how position and velocity are connected with area. And then that's a little bit of a precursor to what's going to happen later chapters where we're going to use these integrals that can solve problems for us, just like we did derivatives, which found maxes and mins and stuff like that. And the hard part of those problems will be setting up the proper integral. Now, I'll be honest, I think that's not nearly as hard as it was with derivatives, to be honest with you. If you want something to look forward to, okay? When I say, hey, we're going to have something like chapter 4, we're going to do max and min, those optimization problems, setting those up was really hard, setting up those functions. A lot of times, I think you'll find setting up these integrals is not nearly as difficult as what that was, okay? But we will be using our calculators a little bit today to go and even do some of these and show you how to do these. But we will have to get the proper integral set up. So we need to know, just the notation and what it all means. All right, then we skipped to number 11, and we were supposed to do these. Now, for these early stages, you were supposed to draw sketches. Now, later on, we won't always draw graphs of these. We'll come up with a lot of different ways to do these integrals. But our next quiz, next week, towards the end of the week, you will be probably drawing some sketches or be given a graph and doing it. Okay, so when we look at 11, hopefully you look at these problems now and you look at 11 and you say, okay, that's just a graph of y equals 4. And, at some point along the way, you'll just be able to do that without even drawing a picture. You'll just say, okay, yeah, that's going to be a dotted line up here at 4. It's going to go from 0 to 3, and it's going to be that. Now, if it says to sketch, obviously you need to sketch. So that answer was what, 12 for 11? Okay, this would be y equals x. Okay, well, y equals x is this line right here, from 0 to 4. Well, that would be this area. It's a triangle. 4 tall, 4 wide, 4 by 4 times a half, since it's a triangle, and that is 8. Okay, number 15, 2x plus 5. Well, that's a y-intercept of 5. It goes up 2 over 2, over 1, up 2 over 1, up 2 over 1, kind of like so. In order to do the area from 0 to 2. Well, that would be a trapezoid. It would be a trapezoid. It would be 5 on this base, and what's this side over here? 9, right? You put a 2 into the function. 2 times 2 is 4, 4 plus 5 is 9. So the area of the trapezoid is 1/2 the sum of the parallel bases. You need to know that trapezoid formula because we'll use it a lot in the coming chapters here. So we take this parallel base plus this parallel base, 5 plus 9, and times the height. Now it's a trapezoid turned on its end, right? It's flipped up. So the height is actually this distance down here. So the height is 2. So when you add that all together and multiply it out, it's 14. Okay? Now 17, what's that graph look like? Upside down absolute value shifted up 1, because 1 minus absolute value of x would really be negative absolute value of x plus 1. So for number 17, we're simply going to have, okay, a V graph upside down shifted up 1. Now, since we know that it has a slope of 1, it's going to cross here at 1, cross here at -1. So the area that they're talking about is just that. But on our next quiz, I think these are basic graphs we need to be able to draw. Linear graphs, absolute value graphs, those kind of things. There won't be a lot of parabolas and those kind of things. We don't know how to do those areas. Things that will make geometric shapes. And that's what we see here. So we're looking at rectangles, we're looking at triangles, we're looking at trapezoids, or we're looking at half circles, basically. All right, so this would have a base of 2, height of 1, so 1/2 times 2 times 1. That would equal 1. All right, then you went over to 18. Now what changes there? I mean, obviously there's an A, but what's that mean? So what would change on my picture? It's still a shift up of A, right? It's an upside down absolute value, shifted up A, and since it's a slope of 1, that would make these points be A and negative A, right? Because it'd be up, down A over A, or whatever, right? Because it's still a slope of 1. So this area on number 18 is just this triangle. Well, what would be the base on this one, this triangle? 2A. So it'd be 1/2 times 2A times A. That's just A squared. So this one would just be A squared. All right. What's 19 look like? Half circle, radius of 3, centered at the origin. And then they also ask us for the integral from -3 to 3. So that's half of a circle. That's 1/2 pi r squared. So 1/2 pi times 3 squared. So that's 9 pi over 2. 9 pi over 2. 9 pi or however you write. Okay? Because it just makes a geometric shape. So this is just the integral between this curve and the x-axis. Okay, well then you go over to 20, what's different? Yeah. And so from -r to r, and there's your radius right there, r. Okay, this is just a circle radius r? Well, what's a circle radius r? It's 1/2, since it's half circle, pi r squared. I mean, that's it. That's just all there is to it. Okay, now I want to show you how your calculator can do that, but that's, on our next quiz, you wouldn't have the calculator for stuff like this. So this, we just want to be able to take these integrals that with just some simple linear or half circle or absolute value kind of graphs that create geometric shapes. Those are the kind of functions that can create geometric shapes where we can easily calculate their area. And then, of course, later on, we're going to go into how do we find areas of other shapes that we don't know about. And that's where we're headed towards. Okay? So if we go here, let's see, let's get a presenter. Amanda Sugar.
You should get a different one.
I don't think I can. It's too late. All right. So go to the calculator screen, please. And what I want, and you guys can all do this on yours. So if you go into the template there where we would normally go to get the derivative stuff, now that's where our integral stuff is. So next to the 9. Okay, and you see the integral. There's a couple of them down here. We want the one with the a and the first one there, the first integral symbol. You'll be going to that one a lot. Okay, so go ahead and choose that one. And let's do, let's see, what was it? It was problem number 15. Let's do the integral from 0 to 2 of 2x plus 5. Now, it puts parentheses around those. Those are not necessary. They just, the calculator puts them in. When you write that out, you don't need to put parentheses there. Your book did too, but it's not necessary. Go ahead and hit enter. And we should get 14, which is what we had, right? Now, Mandy, go ahead and arrow up and grab that again and change those x's to t's. And what do you suppose we're going to get? Same answer. Because the graph of y equals 2x plus 5 is the same as the graph of y equals 2t plus 5, which is the same as 2w plus 5. Now, in the other class, they got a little ahead of me. Go ahead and grab that again. And I told them to change to w's, but then she only changed that last one. Go ahead and change just the last t and the dt. Just change that one to a w. And then hit enter. And everybody look up here, see what happens. We don't get what we're supposed to. Why not? Yeah, so what was a calculator thinking the t was? No, not the variable. The constant. See, the calculator thinks the w is the variable, right? Because we told it with respect to w. So it treats everything else as a constant. So it's treating the t as just a constant. Okay, because remember, an area is a definite integral is a fixed piece of area. It's a number answer. And so this would be a number because t is just some constant. So it would just be a number. Okay, so this has to match that, right, as far as variable. Now, we actually will do some. Let's go ahead and type this one in, get a new integral symbol there. And let's type in the one we did with the square root, with the half circle. Let's type in -3 to 3. And then do square root of 9 minus x squared, or any variable you want. And then do that. Okay, and there it was, 9 pi halves. Now change those to r's. And this is a thing that the non-CAS calculators can't do. See, the CAS calculators can deal with r's and letters as constants, where those calculators cannot. Except you have to do negative r to r. Remember? And these are, I'm sorry, these aren't r's. These stay x's. Those stay x's, right? And our integral though goes. Let's see, what else changed? That's an x. What's the 9 supposed to be? R squared. Yeah, I'm sorry. I meant to change it to like number 20. okay? And change the 9 to r squared. And we should get, what do we have, 1/2 pi r squared? Right, isn't that what we had for number 20? 1/2 pi r squared? We didn't quite get that. Why not? Got absolute value. What did it say in the directions for number 20? It said that A and R are both positive, because why? Well, we were doing the integral from negative R to R, so we were assuming this over here was littler than this, so R had to be positive, so negative R would be negative, right? If R is negative, then negative R is positive, and then they've been backwards, right? So we have to have R positive. How can we tell the calculator that? Where do we put that at the end? So go up and grab that again, and then go to the end, put your vertical bar, and let's tell it that R is positive. And then we get it, right? Then it doesn't have to worry about the absolute value and making that positive, okay? So, so that's kind of cool. So it did that and evaluated that for us as well. All right, so later on we'll be doing a lot of our integrals right here on the calculator screen, but for the next quiz there's probably no calculator, so we'll be drawing the pictures and calculating geometric shapes and stuff like that. All right, let's go to the book and talk about problem 38. There's a lot of, oh, whoops. So, you're off the hook for a little while, Andy. All right, so you may have gotten the answer to number 38, but I think I might be correct in saying that there are a lot of little pieces to this that you really need to get. Yeah. The take-home quizzes to look at. Oh, that's a great question. No.
Are they graded?
Yeah, they've been online for a while. They weren't yesterday.
Our quiz online.
Wait, when did you put them on? 'Cause I'm-
Week ago,
Like,
Nuh-uh.
last weekend.
Been up for a week.
No.
Yeah.
I'm looking.
Hey, you.
No way.
Yeah. No, they have been. Let me double check. Make sure I put both classes up.
You don't want to be able to see those?
I don't, but, and I have to leave for basketball today, but if you ever want to come in and look at it, I'll let you do that. I don't know if I wasn't really even planning on passing back, to be honest with you, but, like in class, but at some point, you can come in and look at it for sure. I've got them. Yeah, they're in there. Yeah, 28 points. They were worth 28 points. All right. So, okay, problem 38 says the velocity of this east-west traveling car is 60 minus 20t. Right? 60 minus 20t. So they wanted us to evaluate an integral from 0 to 4 and describe that in car talk. So I'm going to go ahead and just put the velocity right in there. Okay, now let's draw a graph of that. So here's our velocity curve. 60 is its y-intercept. You just need to be able to know that, okay, this would be a slope of negative 20. So it'll be down 20 over 1, down 20 over 1, down 20 over 1. So it's going to cross here at 3. Okay, something like this for a velocity curve. Now, let's just forget integrals and all that stuff for a second. What would this tell us about the car? Okay, which direction is it going? It's going east to the right. Why? Because the velocity is positive. Okay, so our first thought is because the velocity is above the x-axis, meaning it's positive, means the car is going to the east. But it's positive in getting less positive. Okay, this is stuff we talked a lot about earlier with slopes, right? We haven't talked about it a whole lot, a little bit, but not a lot. So it's positive and getting less positive. So the velocity is like 60, then 50, then 40, then 30, it's slowing down. And so at 3 hours, and I think those are the units, right? Miles per hour here and then hours here. So at 3 hours, the velocity is what? 0. Then what? Turns around and comes back west because the velocity is negative. And the velocity is negative and getting, so what's the car doing? Speeding up, right? And then until 4 hours, it's then speeding up. Now, here we get into this whole thing, velocity versus speed. The velocity is decreasing this whole time, right? Here it is, the velocity graph, and it's going down. So the velocity is decreasing the whole time. But up until 3, the car is slowing down. And after 3, it's speeding up. Yeah, I'm sure, but it's speeding up. So here we've got velocity, we've got speed slowing down, and we got speed then speeding up. But the whole time velocity is decreasing, right? Some of you kind of had that backwards on the midterm when we were talking about that velocity acceleration connection, right? Velocity here is decreasing. The acceleration here is negative, the slope of that, okay? But that's different than speed, all right? Now, they wanted us to do this area from 0 to 4. Well, that would be this area plus that area, right? That would be the integral of this function from 0 to 4. The area, like Steve said, between the curve and the x-axis. So what is this area here? 60 times 3 is 180 times a half. That'd be 90. Right? So this triangle right there is 90. What's this triangle? 1 this way, 20 this way, times a half. That'd be 10, but it's negative. So that down there would be negative 10. For an answer of 80. 80 what? Miles. Right? Because what we have is, think about it here, when I take this 60, which is miles per hour, times 3, which is hours, miles per hour times hours is miles. Now, we've discussed this way back at the beginning of the year, that the area under a velocity graph is actually distance traveled. And I know some of you have already mentioned it in here to me, and a few people in their class have already said stuff to me about the area. Does this have something to do with antiderivative? Well, kind of makes sense, where position, velocity, acceleration is derivative. So if we go from the velocity curve, do the area, it gives us position. We're going from velocity up to position. So somehow that's got to involve an antiderivative, probably, somehow. We already know that if we take the velocity equation and do the antiderivative, that's the position. I mean, we've already talked about that, so that's not anything new. But what is new is how the area is connected to that. Okay? So this gives us 80. Now, you said 80 miles traveled. Let's be more specific. It's displacement, right? Somebody in the other class, the first words I heard was total distance traveled. Well, that's, I mean, in this situation, why is that not total?
He traveled 100 miles.
Yeah, he actually went 90 and then he came back 10. He traveled 100 miles is what he did. So what would, I mean, displacement, yeah, we could use that term. Might be net distance traveled, maybe. Net would be a good term to use. Or just he's 80 miles from where he started, right? He's 80 miles from where he started in this case. Went 90, came back 10. So the 80, so this represents that. Now again, this was velocity. This was the area under the velocity curve. Okay, it was 80 miles per hour. So that's part A. Find the average value of the velocity on this interval. So part B is the average value. Oh, that's that equation we learned yesterday. Average value of a function. The average value of velocity, tell me how to set it up. Integral 0 to 4, which would be the velocity equation, dt. Right? That's the formula we learned yesterday. The average value of a function is the integral of that function divided by b minus a. You've just got to know that. When you hear average value or the average of a function, that is the formula that comes to mind. Okay? It just has to. Well, this is supposed to be average velocity is what this should give us. Okay, well, we've already done the integral, and it was what? 80. divided by 4. Now that was 80 what we said? Miles. What's the 4? Hours. So 80 divided by 4 is 20 miles per hour. Sure enough, that's a velocity. So that's our average velocity. Now we got to really be careful about average velocity. You guys in physics maybe are at an advantage. Anybody taking science and knows about displacement at all would understand this, or this would make a connection to that. If I stood here and went 80 miles or 90 miles this way, and then turned around and came 90 miles back this way, what is my average velocity? 0. Which is strange to think about because I was moving that whole time. How could my average velocity be 0? Yeah, I go here 60 miles an hour, I go here 60 miles an hour, and I get back to where I started, my average velocity? 0. Because average velocity is the net distance traveled divided by time. And if I come back to where I started, my net distance traveled is 0. Okay, if I went for 3 hours and went 90 miles, and then turned around and came back 90 miles, I'd have another piece of area here, and they would cancel out, wouldn't they? And you'd have 0 up top divided by 4, average velocity be 0. So you got to really be careful. Average velocity and speed are not the same thing. So you got to be careful about that. So average velocity could be 0 even though you're moving. Because you move an equal amount in both directions, they cancel each other out. Okay? So that, it says show your result graphically and so forth. And so that's basically what we did. That's the 80, and that's what we're talking about. Okay, now we go to part C. And it says do the integral from 0 to 4 of the speed graph. Now what do we know about speed? Absolute value of velocity. Now, here's our velocity graph. So if I was going to draw the speed graph, what's a quick, easy way to do absolute value of a graph? Take all the negative stuff and flip it up positive. So that means this stuff down here would flip up like that. So this area, so from 0 to 4, we'd be talking about this area now. Well, what is that? That was 90. This was 10. So this answer is 100 miles. What does that represent? Total distance traveled. Now you can put that in your notes right now. We're going to come back to it again. I don't know if you'll remember by the next time we probably talk about it. Maybe it'll be on the next quiz. But if you do the integral of speed, it gives you total distance traveled. You do the integral of velocity, it's net distance traveled. And those two are two different things. Okay? And again, the reason for it is because velocity takes into account direction and speed doesn't. And displacement takes into account your direction, and total distance traveled does not. Doesn't matter whether we turned around and came back, we just want the total distance traveled. And so what happens by doing the absolute value of velocity, everything becomes positive, so all the areas will be positive and everything will add together. Nothing will take away, like it does with displacement. Okay? And then in D, they wanted the average value of the speed. So the average speed would be just this divided by 4, which would be 25 miles per hour. So the average speed would be 25 miles per hour. Okay, which would be a more useful number as far as how fast you're actually traveling. Average velocity is not that useful a number for how fast you're actually traveling because it takes into account the direction. Okay, so anyway, there's a lot right in that problem. A lot that you will see on the AP test when it comes to integrals and velocity and acceleration. Okay, let's go to problem 62. This is what's kind of a difficult problem, one of those that we don't often know how to handle until we've maybe seen something like it. It says that you're supposed to show why this integral, the integral from pi 6 to pi thirds of sine x dx.
Pi halves.
Oh, pi halves? Oh, the pi, yeah, that's pi half. And then it's pi thirds over here. Okay? How do we know that area, that integral, has to be between those two values? Okay? Well, what I was hoping you would do would draw a picture. Okay? And here's a sine graph. And here's pi halves. Now, pi halves is the same as 3 pi 6. Okay? So this would be 2 pi 6, 1 pi 6. So here'd be pi 6 right here. So if I go up to there and up to there, this is the area we're talking about. Right here. Okay, we're talking about that area. That's this integral right here. Pi 6 to pi half. Show why that area has to be between those two. Anybody got a thought? Now, if you flip back a page or two, there's some stuff there that might have made you think of it.
Well, you basically have a trend.
Except this is curved. You know what I mean? I mean, this is curved and not
Still
straight.
kind of estimated.
Yes, now actually that gets into some stuff we're definitely going to do where you could draw a trapezoid in here and do something. But I guess in this problem we're kind of thinking we want to trap it between two different areas, you know, instead of just estimate what it is, right? So Tim's got a good point. If I just connected these two right here and did that trapezoid area, which I could do, we'd have a decent estimate of what this is going to be. But what they're trying to do is trap the area in between two known values. And so this is what they were intending for you to try to do. Now, how would you have thought to do this? You might not have. There is an example of it earlier in the book. But isn't it true that that area has to be between this little rectangle here and the big rectangle here? Right? That makes sense? The area's got to be between those two. So then the idea is, what is the area of those two rectangles? When I say two rectangles, I'm talking about this one here. Right? I'm talking about this rectangle. And I'm talking about the whole big rectangle here. I'm talking about the difference between those two. Okay, it's got to be trapped between those two. So let's do the little rectangle. First of all, what's the base here of that rectangle? That'd be 2 pi 6, which would be pi thirds, right? It'd be the difference between 3 pi 6 and 1 pi 6, which would be 2 pi 6 or pi thirds. So this base is pi thirds times the height. What's that height of that 1/2, right? Sine of pi 6. This is pi 6. Sine of pi 6 is 1/2. So 1/2. So pi thirds times 1/2 is pi 6. That number right there. Okay? We know the area has to be greater than that rectangle. Okay? What about this rectangle? Well, the base of it, again, is pi thirds. And what's the height of the big rectangle? 1. So that's that. And then we know that the actual area has to be between those two. Okay? Not really a big deal there, but it's, if you don't know an exact area, sometimes the best you can do is estimate it or trap it between two known numbers. In this case, what we did is we took this interval, found the minimum point and the maximum point, and used those. That's kind of what that amounts to. All right, let's talk about 71 then finally. They say that f of x is equal to 6 plus x. Mandy, you're going to be up here in a minute. Equals x cubed. And then they also have x equals 0. They want us to find a way to do the area. They'll sketch it first. And then write an integral that would give us the area of this region. Okay? Well, let's graph it first. So we've got y equals x plus 6. So that would be 2, 3, 4, 5, 6. That would be a line with slope 1 that goes up there through 6. Okay, x cubed goes through 0, 0, goes through 1, 1. It would also go through the point 2, 8, which happens to be right on that line as well. That. Okay, so what we would have is, and this is something we'll do a lot here later on in the years, we will have to draw these curves and make nice pictures so that they look decent. But we want the region that's bounded by those three things. Now, where's x equals 0?
Y.
That's the y-axis, right? So isn't that this area right here? This would be the area that's bounded, and you'll get tons of practice with problems that say, find the area of the region bounded by this, this, and this. Matter of fact, if you go back into your old packets, whenever you get those back, some of those problems we skipped, those free response problems, they always had an area problem with several curves and talked about a region that was bounded. Well, this is what you're talking about. We will find that area. Now, why is that different than the integrals we've been doing so far? Not a nice geometric shape, number one, which is why we wouldn't be able to find this area yet, but they didn't ask us to find it. All they wanted us to do was set up the integral.
It's not like an actual integral, because it's not under the x-axis like that.
It doesn't go to the x-axis, which is just what Steve told us at the beginning of the day. Remember, I said, see if you guys remember this, right? Good job. This is not the area from a curve to the x-axis. It's the area between two curves, right? So, there's part A. So part B says set up an integral that would find this area. Now, I'll give you a hint. It's the same thing you would do, basically, to find that area. How do you find that area?
Would be the-
Well, answer this question first.
Well, you do the area of the big circle minus the
Yeah, find the area of the big circle, take the area of the little circle, subtract them, that gives you what's left. So go ahead.
So you have to figure out your two bounds first. So your bound one is going to be where x equals 0, and the other one is going to be where the two functions
Which turns out to be,
meet. That x point, whatever that is.
yeah, it turns out to be 2, 8.
And then
But you're right, you'd have to find that intersection. Go.
And then you do the area underneath the line minus the area underneath
Okay, let me draw this. There's 2, okay. Let me draw that line. So, and I don't think my other colored markers work. I probably got chars. This would be a great time to have some color. No blue over there?
the.
Didn't charge your marker.
All right, sorry for those of you that can't see that, but that's, well, no, I can do that.
Why do you always charge me?
Yeah, because I'm not in here every period.
You didn't trust
Kids,
them.
kids play, I don't trust them, that's exactly right. Okay, so blue, so this area, the blue area here, okay, would be what integral? What integral would be the blue area?
Integral of 0 to 2
0 to 2,
of
6 plus x.
Yeah.
Okay, Mandy, type that in your time. Okay, that would be the blue, what's that? No, just on your phone. Now, that would be the blue area. And then what would be the, and then you said this area? The red area? Because that's the area under the G graph, right? So the red area would be the integral from 0 to 2 x cubed dx. So we have the blue area, and then you said to subtract those. And shouldn't that leave you this black area in here, which is what we want? And that does, I think that makes sense. But an integral, remember, is the area from the curve to the x-axis, right? And we had an area that wasn't that, okay? So to get it, we combine, just like you do in the old ring problem. Outer circle minus inner circle. So we did the whole big area that was blue, take out the red, that leaves us the black. Okay, and then type in that other one, Mandy. And so Mandy has typed those up, and so she did the first integral minus the second integral, left us an area of 10. Now, that would be an okay answer for part B. But also what we could do then is we could take the rule we learned and worked on the other day of how you can split apart an integral. We can do that same thing to put an integral together. So we could write this as a single integral that would be what? 6 plus x, right? And Mandy typed that in. And if Mandy types that in, and we certainly would expect to get 10, but now here's what I want you to think about. The reason we get the same answer is because of that rule we learned the other day, that you can split apart these integrals, and of course it's got to work in reverse. If you can split them apart, you can put them back together. So this gives us 10, then this has to give us 10, but this represents different areas. Forget this for a minute, forget this picture. If I just gave you this integral, what would you tell me this represented? If I just give you this integral and say, what's this represent? You just said the area under that curve, which is totally, this was two different curves, right? This was two different curves with their areas being subtracted. This is a single curve, and it's that area from 0 to 2. Okay, so Mandy, on your calculator, did you get 10? Okay, now let's go to the graph screen and type in 6 plus x minus x cubed. So wouldn't we be talking about this? Oops. So what we'd be saying is with our second integral, that single integral we wrote, we would be saying that this area right here is what? 10, right? That area right there is 10. So two different pieces of area were represented there, but they're both 10, okay? So it doesn't matter. I mean, the answer we wanted was 10. It doesn't matter how we got it, but it's important that you understand the differences there and what those things represent. So here we have a piece of area that is 10, just like on that previous page I had up. We had a different representation. Here we had a piece of area that was 10 as well, but it was the difference between these two areas, okay? So kind of a subtle little thing there that you may not have thought about when we were doing that splitting apart of integrals, okay? All right, so that's kind of an important concept there. All right, well, not a lot more to do. We got to introduce our little activity we're going to do today, and when we get that done, we will be done. We're done. So, here is how we will set this up. Do you remember when we did a little thing on our calculators? We took the sine graph, which looked like this, obviously. That was F. And we said, let's make a chart of the slopes of the sine graph. Okay? And so we said, all right, at 0, and I think we used our calculators to cheat and do it for us. But at 0, what's the slope of the sine graph? It was 1. And then we went to, I don't know, 0.4, I don't know, whatever. About here somewhere. And what's the slope? Well, but I mean, what was the slope? It was less than 1, right? The slopes are positive but getting less positive. So I don't remember what it was. I don't know, 0.32, whatever, who knows. Then we went to like 0.8, right? And we were in here somewhere. And the slope was getting more, like 0.6 something, right? And we kept going. Then we got to pi halves, 1.57 right here. And the slope is what? 0. And then we plotted these points, right? We plotted those points. And what happened? 0, 1, 0.432, oh wait, I did that backwards, didn't I? That should be like 0.6. This would be like 0.32, yeah. So 0.6 and 0.32, and then we got 0, and then they went negative. Then the slopes went negative. And so we plotted that. We looked at it. It was like, oh, wow. It's cosine. And that was the very first derivative rule we learned, right? Derivative of sine was cosine. What we did is we said, because we first learned about slopes, and we said, okay, tangent lines, and we could sketch right over line. And that's instantaneous rate of change. That's derivative. So we learned about slopes. We said, let's make a slope function. Let's make a function that is a plotting of all of the slopes of another function. And we found out it made another function, and we could find its name, and we could do that. So if we took x cubed and plotted all of its slopes, we'd get what function? 3x squared, right? It'd be a parabola that'd be 3x squared, right? That's what a derivative is. It's a plotting of all the slopes. So we're going to do that same thing now. Except we're going to plot what? areas. We're going to plot areas. So what we're going to do instead, we're going to start with a function f. Okay, let's say it was the sine function. I guess we could again. You don't have to write this down necessarily. But let's say we're going to start with the sine function. Okay, and we're going to plot areas. Now, the area under the f graph. Now, this is going to be harder because, yeah, you don't have an area at 0 like you have a slope at 0, right? You have an area between 2 points. So here's what we're going to do. We're going to define our area function to be this. It's going to be the area from 0 to some right edge. We'll make the right endpoint be our variable. We'll take our left endpoint and fix it. Now, it could be 0, it could be 1, it could be 2. We'll talk about what happens if you change the left endpoint. But right now, we're just going to fix the left endpoint at 0, and we're going to make this be that. So then what do I write in here? F of, okay, Richard said f of x. We can't use f of x if we're using x for this. So we got to use something else. So this is one thing that always throws people off, and so we'll keep talking about it. But here's my function, f of x sine x. I can use x over here because it's just describing this function. I could use f of t or f of z or f of w, f of r, it doesn't matter. Okay, but in here, in that integral, I want to talk about this function. I got to use something besides x because I'm already using x for that. So we'll call it f of t dt. Or f of r or something, but I got to use something besides that. And they say, well, why don't you use something else here? Well, because I want my area function to be using x, right? That's what I'm really interested in here is my area function. So this area function, let's call it a of x. I put a little f there just because it's the area under the f graph. But I want x to be the input of my area function. That's the function I really care about here. This in here, I just care that it's the sine function. I don't care about the t there, okay? All right. So very, very important to understand that the input of my area function is this value right up here, the right edge. Okay, so what's that mean? Well, if my left endpoint is 0, what do I get if x is 0? I'd have the area from 0 to 0. What's that? 0. Okay? And then let's say I went over here to about 0.4. Well, now I'd have this area. Right, so that's a little more. So at 0.4, I have an area of, I don't know. I have no idea what it would be. Whatever. Okay? It'd be something. And then if I go to 0.8, it's getting bigger. Right? I got a little more area. Right? And then I could plot these points and see what we get. Right? And see what we get. And it's going to be very similar to what we did when we had when we were doing that with slopes. But that's the idea, this idea of an area function. So we're taking the integral, and there's going to be an x right up here because we're letting our right edge move, and every time we go to a new x for our right edge, we get another area. Just like every time we moved our point, we get a new slope. Move the point, get a new slope. Move the point, get a new slope. That's the slope function, the derivative function. We're going to do this idea of an area function, okay? So I've got a thing to look at here. So I've got it written out here. Here's my line, 3t plus 2. And so this is what we're talking about. As we slide that right edge, right, we're getting more and more area. More and more area. Matter of fact, I've got one right here. We'll look at this on Monday. This point right here is the area plot. Okay? So when I slide this point, so right over here, I don't have any area. Right? But as I come here, I'm getting more and more area. So that point's going up. Going up. When I go over here, what kind of area when I move to the other side? That's negative area, right? That's negative area up until there. Then where do I go past? What happens when I go past there? What's this little piece? That's positive, right? Now my overall area is still what? Negative, because I got this big negative chunk. Remember, it's because I'm going backwards now, so everything's opposite. I got this big negative chunk, but I'm picking up some positive area now, so the area is coming back up. Now I got 0 area because they cancel, right? And now I'm getting, all right? All right, so we'll talk more about that on Monday. We don't want to leave everybody out that's not here today. Spoil the fun. All right, so here's what we're going to do. You're going to get this thing right here. You can work together on this. Now, there are questions on this sheet, so you're going to answer all the questions on this sheet. You're going to fill in the blanks. You're going to be entering values into a table on your calculator. I'm going to send you a calculator document, okay, that you'll be doing this on, and you'll be filling out the questions on the sheet. And then I'm also going to be sending you some quick polls with some of these same questions, and I want you to answer those and send them to me, okay, at various times as we go along, okay? All right. All right, here it comes. Did you get it?